At the turn of the 18th century, craftsmanship across Europe and Russia faced a fundamental technical limitation. Metalworking depended almost entirely on hand-controlled tools, especially traditional lathes. These machines could rotate a workpiece, but the cutting tool was guided by the operator's hands. Precision depended on physical strength, steady control, and years of experience. While this approach was adequate for simple objects, it failed when uniformity and exact measurements became necessary. As societies demanded more complex machinery, the limits of human-guided turning became increasingly obvious. The core problem was inconsistency. No two parts produced by a hand-guided lathe were truly identical. This lack of repeatability caused serious issues in critical fields. Artillery barrels required precise alignment to function safely. Coin dies needed uniformity to maintain public trust in currency. Scientific instruments demanded symmetry for accurate measurement. Even small variations introduced by the human hand reduced reliability. Skilled artisans compensated as best they could, but skill alone could not overcome mechanical instability built into the tool itself. In Russia, this challenge became urgent during the reign of Peter the Great. The state pursued rapid modernization, focusing on shipbuilding, military strength, and engineering independence. Russia needed tools capable of producing consistent components rather than one-off handcrafted pieces. Dependence on imported equipment and foreign specialists was costly and unsustainable. Workshops required machines that could translate motion into controlled, measurable cutting. Machines that embedded accuracy directly into their design rather than relying on the operator's judgment. It was within this environment that Andrey Konstantinovich Nartov identified the true weakness of existing lathes. Through direct work with turning machines, he realized the issue was not power or material quality, but guidance. The cutting tool needed a mechanically defined path. By replacing freehand movement with screw-driven, guided motion, precision could be made repeatable. This insight transformed the lathe from a craftsman's aid into a controlled engineering system, laying the groundwork for a breakthrough that would influence the future of machine tools. Andrey Konstantinovich Nartov was born in Russia in 1693, a period when the country was undergoing deep structural and cultural change. Russia at the end of the 17th century was still largely agrarian, with limited access to formal technical education. Most mechanical knowledge passed through workshops rather than schools. Nartov's early environment exposed him to practical craftsmanship rather than academic theory. From a young age, he showed a strong inclination toward understanding how tools worked, not simply how to use them. This curiosity would later define his approach to invention. Unlike many European engineers of his time, Nartov did not receive a classical university education. Instead, his training followed the traditional apprentice model. He learned by observing experienced craftsmen, handling tools, and correcting mistakes through repetition. This hands-on education gave him an intuitive understanding of materials, resistance, and motion. It also shaped his thinking in practical terms. Every idea had to work in real conditions. This mindset separated him from purely theoretical thinkers and made his later mechanical designs both reliable and adaptable. Nartov's abilities eventually brought him to the attention of the Russian court. During the reign of Peter the Great, skilled artisans were actively recruited to support modernization efforts. Nartov gained access to state workshops where advanced turning and metalworking were conducted. He worked closely with foreign specialists invited by the Tsar, gaining exposure to European machines and techniques. These interactions allowed him to compare Russian practices with those abroad and recognize that even Europe's best lathes still relied heavily on manual control. The limitation was universal and therefore solvable. Historical records of Nartov's personal and family life are limited, but it is known that he married and maintained a stable household while serving the state. His career demanded long hours in workshops and court service, yet he remained focused and methodical. Colleagues described him as disciplined rather than flamboyant, driven by problem-solving instead of recognition. This balance between personal responsibility and professional dedication allowed him to pursue long-term mechanical improvements without distraction. By the end of this period, Nartov had established himself not merely as a craftsman, but as a trusted technical innovator. By the time Andrey Konstantinovich Nartov had established himself in state workshops, he was no longer simply operating machines, he was studying them. Daily exposure to traditional lathes revealed patterns of failure that most craftsmen accepted as unavoidable. Cutting tools slipped, pressure varied, and even experienced operators produced uneven results. Nartov began documenting these inconsistencies mentally, focusing on how motion was transferred from the operator to the tool. He concluded that as long as the cutting process depended on human hands, precision would always be limited. This realization marked the beginning of his deliberate effort to redesign the lathe at a mechanical level. Nartov approached the problem incrementally rather than attempting a complete redesign at once. He experimented with ways to stabilize the cutting tool and restrict its movement to a controlled path. Early trials involved fixed supports and rudimentary guides, but these still lacked accuracy. The breakthrough came when he explored screw-driven motion. Screws converted rotational movement into predictable linear travel. By attaching the cutting tool to a screw mechanism, Nartov could control depth and direction with mathematical consistency. This shift transferred precision from the operator's hands to the machine itself. Developing this system required repeated testing. Prototypes were built, dismantled, and rebuilt. Some mechanisms jammed under load, others wore down too quickly. Nartov adjusted thread pitches, experimented with materials, and refined alignments. He also introduced calibrated markings, allowing the operator to measure movement rather than estimate it. This was a critical step. For the first time, a lathe could reproduce identical cuts repeatedly, regardless of who operated it. Precision became embedded in the structure of the machine, not the skill of the craftsman. When Nartov presented a fully functioning, mechanically guided lathe, its advantages were immediately clear. Compared to contemporary European machines, his design offered unmatched repeatability and control. Decorative turning, complex profiles, and precision components could now be produced efficiently. The lathe demonstrated that machinery could enforce accuracy through design. This achievement established Andrey Konstantinovich Nartov as a pioneer of precision engineering and prepared the ground for modern machine tools that would later power industrial manufacturing. The defining feature of Andrey Konstantinovich Nartov's lathe was the replacement of freehand tool control with a mechanically guided system. At its core, the machine consisted of a rotating spindle that held the workpiece and a cutting tool mounted on a rigid slide. Unlike earlier lathes, where the operator pushed the tool manually against the rotating material, Nartov fixed the tool onto a carriage. This carriage moved along a predetermined path, ensuring stability and eliminating unintended deviations. Precision was no longer dependent on the steadiness of the operator's hands. The key innovation enabling this control was the lathe screw mechanism. The lathe screw translated rotational motion into precise linear movement of the cutting tool. Each turn of the screw advanced the tool by a fixed, measurable distance. This allowed the operator to regulate depth and length of cut with consistency. Because the screw's motion was synchronized with the spindle, the cutting process became predictable and repeatable. This synchronization ensured that identical components could be produced consecutively, a critical requirement for both industrial and military applications. Nartov's lathe also incorporated calibrated guides and adjustable supports, allowing fine control over tool positioning. These features made it possible to produce complex profiles, threads, and ornamental patterns with accuracy previously unattainable. Importantly, the machine reduced the influence of human error. Even a moderately skilled operator could achieve results that once required master craftsmanship. This democratization of precision marked a turning point in manufacturing, shifting emphasis from individual skill to mechanical reliability. The broader impact of Nartov's design extended far beyond his lifetime. By embedding accuracy into machine structure, he laid the foundation for modern machine tools used in industrial production today. Principles such as guided tool movement, screw-driven feeds, and repeatability remain central to contemporary lathes and milling machines. Andrey Konstantinovich Nartov demonstrated that precision could be engineered, not improvised, an insight that quietly reshaped manufacturing and secured his place in the history of mechanical engineering.